So thank you, everyone. Let me share my screen. All right. So I'm going to put a link into the chat. I'm not sure how everyone else will access it, uh, but it's where I've been putting all my material. How do I do this? Give me a second. No. You drop it in. I'm not sure where the chat is. Um, Here we go. Okay. And I'll send it. Um, I'll put it to everyone. So these are the notes that I'll be talking off of. And I also have, there's a GitHub repository for all this. Okay. So if you search here, or if you look up my GitHub, DSN Foundations 2024, that'll be all the material that I talk about today. Okay. And so what I was planning for this session, I prepared these three notes. Kind of in the back of my mind, what I was thinking would be most helpful is I wanted to have some material that's practical, basic ideas from statistics, machine learning that can help you navigate choices of models. And then once you fit some models, know how to choose between them and visualize the results. And I think um, this is not going to be that research oriented, but I think it's the first thing that I do whenever I have any real problem. And definitely important baselines for anything you do with research. We have 90 minutes. So my hope is that you'll ask questions and um, we can have a little bit more discussion because otherwise I think just listening to me talk on a screen for 90 minutes and also me just talking for 90 minutes can be tiring. So I hope that you send questions or if there's any way that you can raise your hand and then someone can kind of share the question with me that way, that would make it a lot more fun, I think. Okay, and let me just check. Uh, I was getting some messages. Sorry, all of this. I'm still not sure how this works. Okay. Okay, awesome. So I just saw that you all got the links. So I'll get started. It goes from bottom up. So the first note is about just how do you set up a supervised learning problem, right? So not talking about any specific models, just understanding the structure of the kind of problem. And I think this is important because it highlights the kind of data that the ways you can think about data for any actual problem. Okay, so kind of my first story is that even though machine learning, we get so much attention when we talk about like algorithms, actually everyone is making predictions all the time, right? It's not just something restricted to machine learning, right? So even things like choose to take the bus to work, right? I'm always in the back of my mind, especially when you live in a cold place like Wisconsin, you think, how long am I going to have to be waiting at the bus stop? Right? And there are actually all sorts of ways in the back of my mind that I'm kind of adjusting my prediction, right? Like if it's very poor weather, internally I might predict there's actually going to be more likely to be some delay, right? So in the back of my mind, there are all these kinds of features of my context that I can use to make a prediction, right? How can you make this a little bit more formal? Like how can I make this question of you know, I'm at a bus stop. I have all these features around me. There's the weather, there's rush hour time, how many people are there. There are all these features of the problem, and I'm trying to predict how long am I going to have to wait, right? To make this formal, you can think of storing that sort of information into these vectors, and you'd write it as this sort of bold X and lowercase y here. So I could imagine doing this every single day, take the bus every single day, and then gather all this sort of background information, like the weather, how many people are waiting there. I could store all that information in these X's, and then I could count. I would use my stopwatch to see how long I had to wait. And that would give me a data set. And so that would give me a 365 length data set. And I could try to eventually use this data set to learn a rule from X to Y. Like I might notice that it's always late on rainy days. Y is systematically longer on the rainy days. Okay. So that's conceptually how I think about prediction, right? You have to understand what are the relevant features of the problem. You have to have a very concrete response, and then you have to learn the relationship between them. Okay, an important distinction are in the types of the variables, right? So if you have continuous data, that would be like um, how many more minutes, right? That's qualitatively quite different from having categorical data. That would be like, is it delayed or not? Yes or no. These two lead to different kinds of problems, right? This first one is called regression. The second one is called classification, right? So yeah, just some more examples here. But if you're trying to figure out patient's disease, whether it will be cured or not, that's classification. Like it's not a continuous thing. You are either cured or you're not. But maybe you're trying to figure out something like crop yield. And then there's like a whole gradation, and you might have a lot of continuous measurements associated with crop yield. In this case, you would be thinking about this as regression. Right? So these are kind of the two main classes of supervised learning problems: regression problems, classification problems. So I just mentioned here that there are actually many other kinds of regression, right? Even though people usually just talk about categorical or continuous data, you could have a response that's, many continuous variables at once, right? So instead of just like a crop yield, maybe you have yield, but also like the health, um, or, you might be trying to predict an entire function or an entire image. Right? And these are also kinds of supervised learning problems. A lot of what we'll talk about today applies to these settings, even though we won't be giving any concrete examples there. Okay, and one of the reasons I wanted to prepare these notes is just to have a lot of pictures that I can share. Because I always try to understand anything just pure text. I try to understand what is that geometrically. So geometrically, what these problems amount to, regression, you can kind of think of as fitting a curve through a collection of points, right? So here's how long I'm waiting at the bus stop. Here's the number of people at the stop, right? If there are a lot of people there, that means the bus is probably coming soon, right? So you expect some sort of decreasing relationship like this. But there's always some noise around there. There's some random variation. Okay. So this kind of continuous regression, you can think of as just there's this continuous y-axis, and you need to fit a curve to that continuous y value. This is how it looks like if you have just one feature. If you have multiple features, then it starts looking like surfaces, right? So this is the same as the previous x-axis here, but now I have introduced a new variable that I've also collected at the time. So maybe if it's telling me something about whether it's rush hour or not, some new continuous variable. Now I can use all the continuous variables to try to make some sort of prediction. Right? So 2D, or like a surface in 3D, 2D surface in 3D instead of just a curve. But it's the same, you can use the same kind of algorithms. Okay, so that's how I think about regression geometrically. You can also think about classification geometrically. So here you have just categorical response, only two possible response. Here it's purple and red. Right, so whether the patient's going to recover or not, maybe you have one feature that you're going to be trying to use to see whether they recover, right? If you only had their blood pressure at some initial test, and then you're going to try to predict whether they're going to recover or not, maybe the people who have lower blood pressure tend to recover, and people with higher blood pressure don't recover. If this is the case, it would look like this geometrically. Right? You have the two classes that they could end up in, the two colors, and then some information that you've gathered, this X information, is helpful for separating the colors. So this is the 1D analog of this for classification instead of regression. But you could also have multiple dimensions. So instead of just having this one dimension for blood pressure, maybe I've measured both the blood pressure and the resting heart rate. And if I have several dimensions, instead of just being color points on one line, I can have kind of color points in 2D. The problem of classification now is trying to figure out where is a reasonable boundary between these two sets, right? If I want in the future, I get a new person who's at a location like here. I've never seen it in the previous data. What should I decide? Do I think that they'll recover or not? Right? If you can decide in advance, maybe that helps save you some time so you don't test a treatment that's not going to work, right? But in order to make a prediction at a new location, you need to have drawn that boundary in advance. Okay, so this is kind of now higher dimensions, and you can continue in as many dimensions as you want. It tends to actually get easier to separate the different groups the more dimensions that you have, because it kind of means you have more relevant features. Okay. Any questions so far? This is the kind of setup for supervised learning. Mm-hmm.
We have a question so far. Okay, we have one, Professor, just a minute.
Sorry,
All
can you repeat a little bit slower? There's a lot of echo.
No, that one doesn't work.
Okay, we have a question for one of the participants.
No.
We have a question.
Okay, yes, I can hear. I can.
Okay, all right, sir. So I'm seeing from your, from your notes that to predict whether someone will have a particular disease, correct, that three variables are not enough. So is
Yeah.
it that the larger the number of variables, the higher the propensity for us to predict that the person will have a disease currently? Or
Okay.
what if we find a particular variable, one or two variables that are potent enough to make the prediction? Must it be a higher number? Yes.
Okay.
All right.
Okay, so if I understand your question correctly, it's a kind of a question of like how many variables do you need in order to get good predictions? Is that the right way to think about it?
Yes.
Or okay. So this is this is going to be context dependent, of course. Um, there's a trade-off that you need to be able to navigate in this question. On the one hand, the more relevant features you have, the better chance you're going to have of being able to separate these different points, right? Like you can imagine an example where in one dimension, you wouldn't be able to split it at all, but in multiple dimensions, you'll be able to split it very easily. Like I can draw a picture actually for you right now. So I don't know if you know like the XOR function. Okay. Can you sort of make out this picture? Right. So I have like a two variables here. If you use only one of the dimensions, then there's no way that you're going to be able to separate the open and the closed circles, right? Because just along this dimension, there's kind of equal proportions of both classes. Just along this dimension, there are also equal proportions of the two classes. But when you have both of them, all of a sudden you can easily separate these two groups, right? You somehow use the fact that when they're kind of both large, both small, you can start making very accurate predictions, right? So in that sense, having more features is better, right? Because like the interactions between them might help you draw better curves. On the other hand, the more features that you have, the more difficult it gets for your algorithm to find a good boundary. You can, even in this kind of 1 versus 2D case, For 1D, the algorithm is kind of obvious. You just kind of trace, like you test many different cutoffs, and then you look at how good that rule would be. So you don't even need anything fancy if you have only one variable. Even with two variables, it gets a little bit more complicated. Like you could have now this kind of curve, and you can imagine that as you get 100 variables, that gets even more complicated, right? So on the one hand, you want to have more features so that you can potentially discover more relevant rules. But the more features you have, the more challenging it becomes for the algorithm. Usually the way to help your algorithm in that case is to give it more and more data, right? But if you have relatively little data, then having lots of features might not actually help because you, even if there is a rule, you might not be able to learn it. Okay. Let me know if you have any follow-up questions or if anyone else has a question.
All right, that answers the question. You can go ahead. Do you have any other question? Okay, Prof, you can go ahead. No other question for now.
Okay. So continuing. So now that we have a kind of a general sense, uh, the problem, I want to describe what I think of as kind of the main classes of algorithms, or at least like statistical learning algorithms. So for any one of these, there are many, many kind of choices, but I find that if you know these general classes, you can kind of cover, they're kind of different enough that if I try one of each of these class of methods, it's kind of a good starting point because um, it's better to kind of consider very different algorithms at the start of an analysis rather than considering like 100 variants of one very specific approach. Yeah. Because depending on the problem, different sets of methods might be better. Okay. So what are the kind of sets of methods that are most relevant? Uh, One is just to think about linear models. Right? It's again one very general class. So the simplest way you can think of drawing a curve is just draw a straight line through the points, right? So this is in the regression case, you have a continuous response. I'm approximating that continuous response by you have some intercept, you have some slope. You're just going to try to find the best intercept, the best slope to go through the data. It looks like this. If you have many different features, then you don't just want one x1, you need to have like an x1 all the way to your dth feature, xd. Algebraically, you would write this as this matrix or this kind of vector notation, B transpose X. And that just parameterizes a surface instead of a kind of 1D line. Right? The relative slopes in each direction, those are the coefficients. So the B1 through BD. Okay. Now, this defines a whole collection of possible surfaces. Every different choice of B you get, you're going to get a different slope and a kind of different intercept. Right? So how do you choose a good B0, B1 to BD? Right? So the usual idea in linear regression is you choose the B that's going to optimize this loss. So what it's saying is you want B transpose X to be very close to Y, um, B, because you think of this is like a distance. This is a distance between yi, b transpose x. You square it so that you can only get positive values, right? If you had not squared it, you might get negative value, and then that's not really a good distance measure anymore. So this is measuring the distance between the points and the curve, and the smaller you can make that distance, the better your curve is to approximating the data, right? This is what you would optimize for a continuous response, right? It's a little bit more complicated if you're doing classification, right? How do you understand distance classification? You can't just draw like a some sort of straight line anymore, right? What you want to do instead is you define something called like a sigmoid function. So this is just saying like a draw, like in this example, I had this kind of arbitrary curved boundary. If you're just doing the kind of linear analog for classification. What that looks like is just you have a straight line that separates the two classes, right? And how do you draw these kind of straight boundaries? You just need to figure out the direction B that's normal to that plane. Once you find that direction B that's separating those two directions, like that's going to be your new rule for separating the classes, right? So this is one way that you can draw this. So here's a function, it's always between 0 and 1, right? When you have really large values of B transpose X, this is basically 0. When you have really small values, like very negative values, B transpose X, then it's basically 1, right? And when this value is exactly 0.5, that is this boundary, and the direction kind of normal to that boundary is exactly B, right? So this defines the logistic regression model. Okay. You have the same problem that we had before. So here, this defined linear regression, but we needed to figure out a way of choosing B. Here, we're defining a logistic regression model, but we need still a way of choosing B. We need a way of choosing this direction. So you can use this kind of loss function, right? So this is kind of the picture of what this function looks like, right? So you have log f here. You have log 1 minus f here. Y is either 0 or 1. It's like whether they recover from the disease or not. And you try to minimize this loss function. Right? Why does it make sense to minimize this function? Okay. Well, you can just analyze these two curves, right? So the red curve, the log 1 minus x, this x-intercept here is at 0. The log x, the x-intercept's at 1, right? So imagine if the 1 is predicted, like if f here is 1, right? Then you're right here. This log f would be 0, right? So if the actual class is 1, and you predicted that it's 1, then you get no loss, right? But if you had predicted that if your kind of probability wasn't at exactly 1, then you get some penalty, right? Because you're going to kind of flip this with a negative sign. So you're going to end up getting kind of, reflect that, that's going to be your penalty for not getting exactly, being totally confident on the correct class, right? And also if you have the wrong label, right, then this will also give you a penalty, right? Um, so to think about that, let's say that it's actually 1, but then we had predicted that it's like we had thought it wasn't going to be class 1. We had given it a probability of like 0.1 of being class 1, right? In that case, you would look at the log of 0.1. The 0.1 is going to be down here, right? So my loss function is going to be whatever that value way down here is. You flip that, you take the negative sign, so you flip that over, that's going to be your loss. So if you had thought that there's only a 0.1 chance of it being class 1, you get a pretty high penalty, right? So that's how you go about choosing the right choice, the right B, right? You find among all the possible directions that you could be having here, all the different ways of separating these points, different choices of B, you calculate this error, this loss for every single one of those choices of B, and then you'll be able to get a better selection. Right? Really, you don't test all the choice of B, you optimize B so that you have the best direction. And you optimize it according to this sort of penalty. Okay. So here's just a kind of concrete example of this, right? So this is some data set that's built into scikit-learn. It's a diabetes disease progression data set, 10 predictors, just how it looks like at the beginning. You have all these different predictors. You have some response variables. The really high ones, this is kind of high disease severity. So it's like the diabetes got worse. the lower values, this means the diabetes is still not as bad as it would otherwise be. Right? So they make it pretty easy to choose this value B, right? So this is a continuous response. So we're going to use linear regression. So you can use this linear regression module. You fit X and Y. Inside, under the hood, it's solving this optimization. It's these squares. And it gives us these coefficients. Okay, so what it's saying is like this first variable, I didn't explain what all the different predictors are, but it's saying if you increase this first predictor, then it's actually good. You have like a lower disease severity in your prediction, right? And then like these last few, if you increase those predictors, you tend to have, it's an increasing slope in that direction, so you have higher disease severity there. But yeah, just practically, it's just a few lines of code, right? Once you have your X, your Y, you can just run the fit. It gives you coefficients. This on its own is not that transparent, right? We're going to see some examples in a couple, maybe like an hour from now. You'll see a concrete example of how you visualize this a little bit better. Okay. Do the same thing with logistic regression, right? So this is going to be a classification problem instead of a regression problem. So we need to have yeah, there's kind of specific outcomes. So what you're trying to do here, there are three types of penguin. That's why it's classification, categorical response. Three types of penguin. We're going to be using a couple of the features about the beak. Right? So it's like how long is the or how long is the beak? How tall is the beak? They have all sorts of other variables too. Like is it a very big penguin, very small one? And then you can try to figure out what species it is. Okay. So I just read in some data here. Uh, this is not even fitting a model. I'm just making a plot, right? And just eyeballing it, it looks like you can pretty much tell the difference between these penguins using even just these two features, right? Uh, the light green, the Adelie penguins tend to have shorter bills than the others, right? And actually, you kind of need both of these features to be able to tell, right? If it had only been using build length, then maybe you would cut it over here, but you'd get a lot of errors. You would get a lot of these, some of these Gen 2 penguins have short bills as well, right? So you really do need the two features here to draw the boundary well. Okay. Again, using scikit-learn, instead of using linear regression, we use logistic regression. There are a few data points with missing values, so I drop NA here. And then it's the exact same kind of code from before. I just run fit. Okay. Instead of looking at the coefficients, I'm getting the predictions. So here, this returns to me the fitted y hat values at the original predictors X. Okay. And then the color here is the true species. And then the panel is what the model thinks it is. So in general, the colors are pretty well separated across the panels, but you can see a couple errors, right? So like there are these penguins here. They're actually chin strap penguins with very short bills relative to the other chin strap penguins. And the model mistakenly classifies it as Adelie, right? And same out here. There are a couple of misclassifications. And they tend to be at the boundaries, which kind of makes sense. Like when you're at the boundary between the different clusters, then there's some ambiguity about what the label should be given what inputs you have. Right? Okay. So that's just plain linear models. Now, a little bit more advanced. For a lot of problems, you actually will have many, many features. So this is just two features. Like you don't need to do anything too fancy. But what if you had 100 features, right? In that case, you might think that a lot of the data you gathered might be irrelevant to the problem. So you can actually improve your modeling if you tell the model I gave you 100 features, but only a small number of them are probably relevant. Like you can ignore the rest of them. If you give your model this information, you can actually get much better prediction performance, right? Because it doesn't have to search through kind of as complicated a space if you tell it that only some of the features are relevant. Mathematically, how do you tell a model that only some of the features are relevant? You can write down the same kind of linear model as before, but now you tell it that only some of the coordinates, only some of the B coefficients should be non-zero. Everywhere where it's zero won't have any influence on the prediction. So this is called sparse linear regression. And this is the picture that I have in mind. So variable one, this would be a non-zero V. It has some actual influence on the response. This is a variable where the B should be zero. Changing this variable has no influence at all on the response. So this is kind of the advantage of using sparsity. You can throw in more and more relevant, or you can throw in more features, many of which are irrelevant, and the model will discover on its own that some of the features are irrelevant, and it will set those features to zero in their coefficients. Okay. This is the picture is for linear regression, but the same idea applies to logistic regression. This is the picture for logistic regression. It's saying um, this variable, this direction is useful, but this direction is not at all helpful. So it's just going to ignore this dimension when it makes the prediction. So that would be that coordinate of B would be set to zero. How do you implement this? Again, using scikit-learn. Okay, what is this data set, first of all? It's a baseball data set. It has all these characteristics of the baseball players. So it has their salary and also just like how good are they? How many home runs did they have, say? Um, you can imagine, there are tons of features here. Maybe only some of them are actually relevant to the player's salary. Okay. So here I'm just separating the data. This I'm going to be calling my response variable. Everything out here are my predictors. And then I give it, instead of linear regression, now I'm using an elastic net regression. So elastic net is the kind of model in scikit-learn that you use to allow for some sparsity in the fit. Okay. Um, Alpha and L1 ratio uh, is mainly this or both of them are kind of relevant for the sparsity, actually. Like larger values of both will encourage sparser fit. There's a little bit more subtlety in ElasticNet because it's not just sparsity that it's trying to promote, but this is a detail we don't have to worry about now. The more important thing is once I fit it, and then I look at the coefficient. So a lot of the coefficients are now exactly zero, right? So it turns out that at bat, this first feature is just not important. It's just not really related to salary at all. But the number of hits is. Number of hits definitely has some influence. Okay, so this is how you read it out. It's like the ones where they're zero, those features aren't helpful for prediction. The ones where it's non-zero, those are useful. Okay. Also notice here, I extracted the model predictions. And these are just the relationship between the true and the predicted values. What if I added a picture? Yeah, okay, so here's the picture of the true versus the predicted value. Right? True salary, predicted salary. It's not perfect. Maybe having even more features would do even better, but at least there's some reasonable correlation. Right. Okay. So those are linear and sparse linear models. The final kind of class of models I want to talk about now are tree-based models. So again, I'm mentioning it because it's kind of like a totally different family of models. Um, there are situations where like, trees would work really well and sparse linear regression would work really poorly, and vice versa. There are situations where sparse linear regression works great and then trees would be poor. So it's hard to know in advance which of these classes of models work well. So instead, I generally try like one simple version of each of these models, and at least it'll narrow in like this set of models might be worth spending more time with. Okay, so they're doing a different kind of curve, but it's a little bit less obvious the kind of curve that they draw. So instead, let's think about this kind of picture, right? If you thought about this traffic and this bus stop problem again, maybe if you weren't thinking, if you weren't a mathematician and I asked you like, how do you make a decision? How would you estimate whether it's going to be delayed or not? You might not draw any curves. If you weren't a mathematician, maybe the thing you would think about is some sort of diagram like this, where you come up with a list of relevant features and then you draw like a tree that says, if it's weekend or not, that's a really important distinction. So I think that if it's the weekend, you're gonna have to wait a lot longer, right? So any of the possible directions for weekend, they're gonna be taking quite a long time, like half an hour wait. Versus if it's a weekday, and if there's no traffic, then it might be a very short wait, right? So this is how I think like a kind of um, non-mathematical description of the problem might work is you think about the relevant features, and then you just make a diagram depending on, if it's not weekend, you go down this you go down this branch. And if it's not weekend and it's not raining, you go down this branch. Versus if it's not weekend and it is raining, you go down this branch. Right. And then you just kind of draw this sort of diagram and get here's your best guess given that you've gone down a certain path on the diagram. Okay. So we'll call these the leaves. Um, right. And this can be used either regression or classification, right? You could imagine a situation where if it was the disease one, it could be like recover, recover, don't recover for all the different leaves. Right? So the same kind of branching logic works for either regression or classification. Okay. Now it turns out that this is actually drawing a curve in the data space. And how can you realize that? Kind of think about a very simple tree. You just have one set of splits, right? So traffic is small, traffic is high. This is kind of equivalent to drawing one dimension that's the traffic dimension, and then having a curve that's just two values, right? So it's 30 when it's high traffic, and it's 10 when it's low traffic. And how do I define high versus low traffic? I use 0.9 as my cutoff. And so in a sense, there's an equivalence between this tree and this one-dimensional curve. Okay. So this is kind of the main insight. This sort of curve, now we're starting to think uh, like these sort of curves again, except, instead of these sort of linear things, we have these sort of kind of thresholded looking curves, right? So it's at a threshold, you jump, and then you're constant again. And if you split another time, you actually can start getting kind of not just 1D threshold kind of curve, you can start getting these 2D partitions, like rectangles in a higher dimensional space. So like how did I get at this picture? Right. So first I split rain small or not. So I cut at rain is 1. Everything above, when rain is above 1, you're going to have either 14 or 30 minutes. So that's this 14 or 30 minutes. Everything rain is less than 1, you have either 4 or 6 minutes. So that's exactly rain is less than 1, I have either 4 or 6 minutes, right? So that's this kind of first split. And then for the one, say, for example, the rain less than 1, I divide that rectangle again. I divide that rectangle according to traffic small or traffic large, right? So given that rain is less than 1, I'm in this region. Given that rain is less than 1 and traffic is less than 0.2, that's traffic is less than 0.2, that gives me this region right here. So that's where I get the 4 minutes from, right? So now you can think of this as like 2x input, and then you have flat pieces along the different rectangles here, right? So instead of flat pieces in one dimension, you have flat pieces in 2 dimensions on top. Mm. And that's the idea for decision trees. Okay. And now you might have heard of like random forest or gradient boosting models. These are just kinds of models that learn many, many of these kinds of trees and then average the predictions across all of them, right? So it turns out that by averaging lots of these trees, you can get better performance. It does a kind of stabilization. So just showing how you can do that in this code. Mhm. So again, scikit-learn. What's nice, scikit-learn is nice because it kind of uses the exact same syntax for all the different kinds of models, right? So I just, instead of using linear regression, yeah, instead of elastic net or linear regression, I just use gradient boosting here. But otherwise, it's almost the exact same code. And now if I do the prediction, it actually gets perfect training performance here, right? And it's because it doesn't have to draw these straight lines, right? It can draw kind of more complicated, like if we go back to the original data. Oh, I guess I didn't draw the original. Oh yeah, here, right? So if you look back to the original data, you might want to draw kind of rectangles that separate it a little bit more than just a straight line, right? And that's what's going on here, right? Since it's able to draw these more complicated rectangles that are separating it, it's able to get kind of full training performance. Okay, so a bunch of models. Conceptually, how do I just navigate them? Right. This is kind of the diagram I keep in my mind. So if you don't have very many features, you are fine just using linear or logistic regression, right? You don't need to worry about setting some of the coefficients to 0 if you have not that many features. The color here I'm saying is like this is for continuous response. So this is regression. This is for classification. This is categorical response. Okay. If you have many, many features, if it's in a high dimensional setting, you have more kind of, it can be a little bit more complicated to choose. The main distinctions are if you want to do some sort of linear model still, you can do the sparse regression methods that I mentioned earlier, right? So these are the sparse versions of those. It just means that the coefficients for some of the variables are allowed to be exactly 0. Okay. If you think that there might be some nonlinear pattern, right, then you should use this sort of rule. This is no longer linear at all, right? These are the tree-based methods. I've drawn them in purple because it works for either classification or regression. Okay. Then I have just um, some general ways I trade off between them, right? So kind of main strengths, linear, sparse, linear models, they're very fast. They're very easy to interpret, but then they can be maybe not as expressive, and sometimes they can be a little bit unstable, right? Tree-based methods, they can fit very nonlinear things, but they can be slower and they might be a little bit trickier to interpret. There are more and more tools that are out there now for trying to interpret tree-based models, but it's still a little bit of a kind of developing area. Okay, so I have some questions you can test your understanding, and then there's some answers below. But in the interest of time, maybe are there questions about these notes before I move on to the next one?
few thoughts that so Professor Kris has shared. Any question? Prof, we have one question. It's fine. Okay, thank you very much for those foundations, helping us to understand how this model works. I really appreciate it. I have a question concerning when you're talking about sparse linear models. You try to say that for the linear and logistic regression, it will only work if you have a few features, or if you are to be space, if you have more features, there is that use space. But when you were showing it, you from the results, when you were showing it from the coefficient, you said the one that has zeros that will easily take away those features. And you were able to identify, I'm trying to look for it, you're able to identify a particular features. I couldn't get how you identify that feature because I look at the coefficient shown and I try to count the number and the number of features that we got. So I don't know if you could explain if it's possible that part. I don't know if you get the question.
All right. Can you repeat a little bit more slowly? I'm still getting a lot of echo. I understand you're asking about sparsity in the linear and logistic regression. And is it that you're wondering like how do you
Yes,
use the
from the
sparsity?
features, I can see now when the model was imported, baseball, and we have player salary. We are trying to predict the salary of the baseball players. And you said at bats, you said is the one that has features, that has the coefficient, model coefficient after the elastic net was fit of zeros.
Mm-hmm.
Like how were you able to I look at the coefficients
Uh-huh.
from so if you could help in that please, I really appreciate it.
Like like how does it get these exact zeros?
No, from the model from the coefficients, you're able to say the column three, the one that has zeros all through, and you're able to say that shows that the feature at part is the one that is having that zeros. So I don't
Right.
know.
Okay. I think I understand, but and then follow up if my response isn't quite right. So kind of part of the question is like how do you interpret these, right? Um, so or like when I see the zeros in these coefficients, how does it help me understand the features that are relevant here? This is muted. This mic. I don't hear this mic.
Prof,
Or maybe if you type it in the chat, I could read
my
it too.
next question, are you saying how was he able to identify, or how was he able to, from that particular picture, the advert to zeros?
Okay, so like how does it know which to be zero?
Like, how did I identify the best features and
Okay,
then go for other ones and adverts to zero?
okay. So this is a little bit more detail than I put in my notes. But the way it actually does it is it adds a penalty to the coefficient. So we can go back to like the uh, the loss functions here, right? So here, the only thing it's trying to optimize is just, does it fit the data well? Does like B transpose X go through Y? But you can imagine adding to this penalty something that counts the number of non-zero features, right? So you could say, not only does it have to go through the data, it also has to have relatively few non-zero features, right? So you modify this loss function so that it's both having to fit the data and have relatively few coordinates that are non-zero. Usually this is done with an L1 norm. So L1 norm is the sum of the absolute values of the coordinates. And that has the property that when you try to penalize that, when you optimize that with a penalty for the L1 norm of B, then it forces many of the values in B to be zero exactly, right? And since you're still trying to fit the data, it will have a preference for setting to zero the coefficients that are not as important, right? So like if there's a feature that's extremely important for fitting the data, then even though I'm penalizing the number of non-zero coefficients, it will still be included in the fit because it has to fit the data still, right? And you can actually tune the relative weight of how important is it to fit the data, how important is it to have a very sparse coefficient with this L1 penalty, or sometimes people call it like a lasso penalty. Right? So that's how it actually solves it. You modify this loss function to have an L1 penalty that forces a lot of the coordinates to be zero, and it will only choose the ones to be zero, which are not as important for using or for fitting this part of the loss. I don't know if that answers your question or if there are any other questions.
All right, so please go ahead. We have about 10 minutes of invisible time.
Ah, okay, okay.
Thank you very much.
So I had thought we have longer, but maybe I'll start. Um, Let me do. I think this one is more interesting, right? And it's not too long, right? So just kind of continuing on the previous theme, right? So from the previous one, you know how to choose, or like you know that there are different kinds of models, um, and that they kind of amount to some sort of curve fitting. But then there's a subtlety that I left out, and it's that um, just fitting a curve through the data set that you have doesn't necessarily mean it will do well on a future example. Hmm? Okay, I think just some background noise, right? So just this kind of example here, same data set from before, but now this curve just interpolates the data. And you imagine this curve is actually not nearly as useful as the ones that we drew before, which kind of smoothly go through the data. The reason why it's not as useful as before is like you can kind of compare if I had a new example, if these kind of gray points are new data points, you actually get quite high error when you use this rule, which just interpolated the data. The length, the blue line is relatively high here, versus if I had drawn a smooth curve, right, then the length of the blue lines for the new points is relatively small, right? So somehow, even though this looked great on the data set that you had originally, it doesn't generalize to new examples. Versus this one, even though this doesn't look perfect on the original data, it doesn't exactly go through all the points in the original data. On a new example, it will do relatively well. It's kind of, they're all close on the new examples. Okay. So I know you can maybe debate like, oh, did I just draw it to make it easy for this rule? But it's actually a general principle. Under kind of you can prove in more general settings that a smoother class for a lot of different distributions is going to have better generalization performance than something that's very kind of highly jagged like this. Okay. So I drew this for regression, but the same idea applies to classification. Okay, so this one's very jagged, rule doesn't fit very well, or it doesn't generalize very well, even though it fits really well on the original data. This one looks maybe not as good on the original data, but it will actually generalize better, right? You don't expect, like probably if I had a new point here, it would more likely to be purple than red. Just this one point in the training data happened to be red in this area. Okay. So this is called overfitting, right? If you have this interpolating the data, that's like an overfit model. And we need to have some sort of way of choosing the right level of complexity, right? If you make it too smooth, like you can imagine it starting to make it a straight line, that's like the simplest version of a curve fitting. The straight line, it's not going to do as well in this sort of smooth curve. But on the other hand, if you make it too flexible, then you run into this sort of problem. So there's kind of a whole continuum of different levels of complexity, and you need to be able to navigate that continuum. And the usual way that you can do this is you do some sort of training test split, right? So you divide your data, purple, these are the training ones, pink, these are the test ones. And then for any choice of models, you can evaluate the error for that particular choice of model on the test ones, the ones which weren't used to train the model. And that gives you a proxy for what the actual generalization would have been if you gathered more data, right? It's not quite as good as getting actual new data, but it's a pretty good replacement. Okay. You choose in the end the model which has the best performance on the test. You can improve on this a bit, right? So train test, you only have one split. It only gives you one estimate of how good the generalization would have been. If you want to get a better estimate of the generalization, you can try aggregating this many times, right? So one simple way of doing it is just divide the data into k groups and then train on one group, evaluate on the other, and then hold out a new group, train on everything else, evaluate on the one that's left, right? And you do this every single split. Now, instead of having one test error per model, you have k different test errors for each model. Then you can compare the kind of many estimates of the test error for the different models, and then you choose the one which seems to be good across many of the holdout folds rather than just one of the holdout folds. Okay. There's some sort of subtleties here, right? So mm, I've seen people where like they have temporal data and then they apply cross-validation to the temporal data. But then you get some sort of weird situations where you try using the future to predict the past, right? If you just randomly split the samples and they're ordered by time, sometimes you might end up with test points which are earlier than the training points. And that doesn't really make sense, right? That's kind of not representative of what you would actually have in the real world, where you need to have seen, like, if you're gathering new data and it's ordered by time and time matters, then you should be trying to predict future, not trying to predict the past, right? So in that case, you should be doing something called temporal cross-validation. Like you split into time segments rather than just randomly assigning a training test to the original data. Okay. There's also a kind of bias that you get when you use cross-validation. Intuitive way to think about it is like, since you are holding out some of the data, you are not estimating as good a model as you could have if you had used all the data. Like if you use all the data to train your model, you're going to have a better model than if you only use some of it, right? So generally, the error that you get here on this holdout fold, it's going to be a higher error than if you had used all your data. Right? So there's always that bias when you use cross-validation. Mm. And then code, again, using scikit-learn, the main function to know is called train test split. Right? There's also cross-validation we can use. Right? Uh, this just divides the data into now, instead of just X and Y, we now have train and test for both X and Y. I fit my model only using the training data. And now I can look at the performance on the test data. Right? So remember, this is the example where when I used gradient boosting, I got perfect training performance. And again, when I split the data, I still get perfect training performance. But when you look at the test performance, there are now a couple of errors in the test. Right? So this suggests like we had maybe overfit slightly on this data set where uh, if we had thought that going ahead, we would always get perfect performance, that's not true, right? If we had gathered data from new penguins, we were going to get some sort of errors. Now we can understand how many errors we would get. And the reason we can understand it is because we've done this sort of train test split. This is a much more honest way of approaching it. Okay, that was just one train test split, but I mentioned like it's better to average over many splits. And then you can do that using this cross-val score function. And it actually does all the cross-validation under the hood. It just gives you the performance right out of the bath or right out of the function. So it's saying on some of the splits you got perfect performance, but on other splits you got maybe only 90% performance. Okay. And all this is getting at this general principle called the bias variance trade-off. There are models where if it's a very, very flexible model, it will have low bias. It will be very close to the truth, but you might have a lot of trouble finding the truth. You'll have these very noisy estimates around the truth. So this is a situation where it's low bias and high variance. Here's a situation where you have kind of very high bias, but lower variance. So like your model isn't very close to the truth, but you tend to have very stable predictions every single time. Like it's always consistently off. So this is a lower variance, but high bias. The ideal model is you have low for both. And you want ideal in both. Um, Sometimes you do get that. Sometimes there are models with have low bias and low variance, right? Depending on the problem setting. But often if you have like one type of model and you're just trying to look at different levels of complexity for that one kind of model, then you do tend to encounter this sort of trade-off. Okay. And just a final kind of little practical tidbit that I would give is I think it's often useful to just first overfit the data, right? Because when you overfit the data, then it tells you you have enough information in your data set to try like having a chance of making the prediction as well. If you can't even overfit the data, then that means you might need to gather kind of better features. You might need to gather better data, right? If you can't even overfit the data, then there's just maybe not enough signal. Once you've overfit the data, then I try to think you can try to regularize it, add sparsity penalty, force it to be a little bit smoother, make the model simpler. And then that kind of brings the model back to being a better generalization performance. But at least if you do this strategy, you know that you're not trying to optimize something that doesn't even have a chance of being effective. Okay, so that's all my notes for now. I'm happy we can take questions. Feel free if you have any questions when you run, these are all different Colab notebooks, right? So you can try running all the code examples I just had now on the Colab, and all my notes are on the GitHub. Welcome people to reach out anytime. Thank you.